Researchers have long been accustomed to examining climate change research from traditional perspectives. Today, we proceed from the dimensions of planetary orbital variations to elucidate the core issues we have continuously explored for over a decade. How planetary orbital variations profoundly influence the distribution and evolution of Earth's atmospheric water vapor. First, let us consider several key questions. The first question: are the seasonal successions of Earth primarily determined by the geometric characteristics of Earth's orbit around the Sun, axial tilt, eccentricity, precession, etc.? The answer is clearly affirmative. Since the seasonal variation of atmospheric, which is fundamentally determined by Earth's orbital parameters, it follows that seasonal water vapor dynamics are also primarily driven by planetary orbital variations. This point is beyond doubt. The second question: since water vapor variations at the seasonal scale are primarily determined by the orbit around the Sun, we can logically proceed to a further inquiry. What mechanisms dominate the monthly, daily, and even hourly variations of atmospheric water vapor? Conversely, when extrapolated to longer scales, what determines the interannual, decadal, and even centennial variations of atmospheric water vapor? Based on the logical conclusion of the first question, a consistent inference can be derived. At different timescales, the variations of atmospheric water vapor are primarily regulated by planetary orbital factors, though the specific dominant orbital parameters and their manifestations vary. Short timescales, hours gives days gives months, are primarily influenced by Earth's rotation and the lunar gravitational orbit. Seasonal scales are primarily shaped by Earth's axial tilt and its orbital motion around the Sun. Interannual and longer scales involve the superposition and slow evolution of factors such as the eccentricity, precession, and precessional cycles of various planets, as well as broader planetary perturbations. The core concept of this study is to treat the variations in Earth's atmospheric water vapor as an integrated phenomenon, systematically analyzing from a multi-scale perspective which specific planetary orbital parameters dominate and shape the dynamic evolution of Earth's atmospheric water vapor. Detailed methodological validation is provided in the manuscript. Here, we focus on the primary results. As shown in the figure, on a daily scale, Earth's rotation dominates atmospheric water vapor variations. Earth completes a 24-hour rotation cycle, while the Moon's orbit about 27.3 days. Earth's orbit about 365 days. And other planetary orbital changes are relatively minor on this timescale, making rotation the primary driver of daily water vapor changes. Variations in land-sea distribution cause differences in solar radiation intensity across regions, shaping diurnal climate patterns and associated water vapor fluctuations. Analysis shows that water vapor variation curves for consecutive days are highly similar, with minimal amplitude changes, reflecting the consistent periodicity of Earth's rotation and its stable regulation of daily water vapor. On a monthly scale, Earth's rotation completes one cycle daily. The Moon's orbit completes about 1/27.3 of a cycle. Earth's orbit advances only 1/365th of a cycle, and other planetary orbital changes remain minor. Daily water vapor fluctuations caused by Earth's rotation are minimal, making the Moon's orbit the dominant driver of atmospheric water vapor variations. The Moon's gravitational effects on tides and atmospheric circulation became evident at this scale, with its periodic changes shaping intermonthly water vapor distribution patterns. Though modulated by Earth's orbital baseline, leading to inconsistent monthly patterns. On an annual scale, Earth's rotation completes one cycle daily. The Moon's orbit completes one cycle monthly. Earth's orbit advances about 1/13 of a cycle per month, and other planetary orbital changes. Earth's rotation and the Moon's orbit, completing multiple full cycles within a year, have stabilized effects. Thus, Earth's orbit becomes the dominant driver of annual water vapor fluctuations. Its elliptical orbital motion determines seasonal variations in solar radiation, directly shaping global water vapor distribution and circulation, and forming distinct seasonal climate patterns. On an interannual scale, Earth's rotation, the Moon's orbit, and Earth's orbit exhibit similar periodic repetition, their combined effects setting the baseline for water vapor variations. However, differences in other planetary orbital positions emerge at this scale. Some planets complete full cycles, while others complete only partial cycles. These differences disrupt the complete repeatability of interannual water vapor changes, causing variations in water vapor distribution at the same time each year. Notably, the Moon's non-integer orbital period, about 27.3 days, combined with asynchronous changes in other planetary orbits, makes interannual water vapor fluctuations highly dependent on the collective orbital states of all planets. This explains the variability of weather patterns, which rarely repeat exactly. Through above analysis and physical reasoning, as shown in the figures, we have concluded that water vapor changes at different timescales are primarily driven by the orbits of planets at different hierarchical levels. Daily scales are dominated by Earth's rotation, monthly scales by the Moon's orbit, annual scales by Earth's orbit, and interannual scales by the combined effects of other planetary orbits. From a spatio-temporal perspective, hourly water vapor changes are snapshots of the 24-hour cycle. Daily changes form points on the monthly scale. Monthly changes reflect stages of Earth's orbit, and annual changes are units of the interannual scale. Small fluctuations in higher-level orbits often trigger significant changes at lower levels, creating a top-down driving effect. Based on this, we developed a mathematical model to quantify the contributions of planetary orbital changes to Earth's atmospheric water vapor. Detailed analyses and results are available in our paper. Finally, we include the background of prior research related to this study conducted by our research team. Our team has accumulated over a decade of research in this field and, for the first time, systematically studied the overall changes in Earth's atmospheric water vapor from the perspective of planetary orbital variations.